Lecture 7, Module 2, DMAIC, Analyze Stage 2. Verifies cause and effect. Test for non-normal data. We've looked at hypothesis testing and the t-test and z-test and ANOVA, and now we'll look at the non-parametric, or the test for non-normal data, the one-sample sign test, Kruskal-Wallis, and the Moods median. So what if the data are not normal? Using the median instead of the mean. If we cannot use the mean due to excessive skewing or other non-normal behavior, we can turn to using the median instead for analysis. The median, again, you should remember, is the point where 50% of the data is higher and 50% is lower. We can use a very similar formula to the one that we use for the mean. This is n plus 1 divided by 2, plus or minus the z-score times the square root of n divided by 2. To use this approach, we turn to what are called the non-parametric tests. In Minitab, these are found at non-parametric tests, and there they are listed there. One sample sign, one sample Wilcoxon, Mann-Whitney, Kruskal-Wallis, Moods median, etc., etc. Now there are a number of tests using the median very similar to the tests for the mean. The one sample sign test, which is used to compare one median against a known or historical median, similar to the one sample t-test. Kruskal-Wallis test, which is used to compare two medians with no outliers, very similar to the two sample t-test. And the Moods median test, which is used to compare two medians when there are outliers, again similar to the two sample t-test. So let's assume our hypothesis is, and we'll do a one sample sign test. Our hypothesis is that we have made a change in a raw material in the belief that this will help reduce the levels of impurities in our active pharmaceutical ingredient, which have historical medians of 0.35%. We have collected impurity data now on the last 30 batches since the change and want to know if this has reduced the level of impurities. The historical impurity data area are not normally distributed and have a median of 0.35%. Due to the non-normality of the data, we cannot use the hypothesis test for the mean, so in Minitab we select the one sample sign test from non-parametric. Set the test median to 0.35 and the alternative hypothesis to less than, which is what you want to see that it is less than now. In Minitab, it gives us the following output. Sign test for median impurities after raw material change. Sign test of median, 0.35 versus less than 0.35. So Minitab states our null hypothesis of the median is 0.35 and our alternative is less than 0.35. Minitab then states that of our 30 samples, 17 were below our test median of 0.35, none were equal to it, and 13 were higher than it. Our p-value is 0.2923, which is greater than 0.05, so we accept the null hypothesis that there is no difference for the impurity level between the 30 batches after the change, since the median was equal to 0.3288, looks smaller, but it's not. And the impurity levels before the change, median 0.35. There's no real difference between these two. Now, how different are the data? We'll look at the Kruskal-Wallis test. In this case, we're trying to improve the overall production of cases per shift of product on a packaging line by making improvements to an SOP on the operation of the case packer. We collected the production data for 15 shifts before and after the SOP improvement. A box plot shows that the data are not normally distributed, so a non-parametric test is required. The Kruskal-Wallis test is a non-parametric version of the one-way ANOVA. Minitab compares the two sets of data and gives the session window output below. Minitab shows the summary descriptive statistics for the data. The difference in the median cases is plus 25, so it appears that there is an improvement in this change. However, the Minitab calculates the p-value and it is greater than 0.05, so we cannot prove there is a difference. We must accept the null hypothesis. However, going back to the graphical analysis, we noticed that our box plot indicated that there were outliers in the data sets. While the Kruskal-Wallis test is a very powerful test and can be safely used with a wide number of distributions, it is not robust to outliers and may give unreliable results. So in this case, we should try using the Moods median test, which is not as powerful as the Kruskal-Wallis, but is robust to outliers. So here we run the Moods median test with the line 5 total cases versus the SOP change. Again, the difference in the median cases is plus 25, a possible improvement. But again, the p-value is greater than 0.05, so again, we accept the null hypothesis that there is no difference. Moods median test provides a crude graphic showing the confidence intervals for the medians, and we see that they are overlapping. Once again, it's always good to run graphical analyses first to take a look at what the data is saying to you, and then back that up with the statistical analysis.